Welcome to our seventh lecture about energy. This time we will concentrate on the topic environment. The environmental impact of energy consumption and use is very high, and so we will go into some details. We look how the land use of energy technology is. We look into air pollution, the greenhouse effect, and about the waste. So these are the main topics where the environment is touched. There are many other things that the environment has some contact with energy production that can't be covered by this lecture, but let's see. So let's see the first technology that is widely used, and especially in Germany. It is the lignite coal. This is a type of coal that is a very low energy efficiency, as we have already seen in the last lecture, where we talked about the different energy commodities. We've learned that lignite coal has bad impact on the carbon. And beside that, there is also another problem. And this problem is due to the way how this type of coal is produced. And there are the basic process is the so-called open pit mining. That means the coal is in the underground. It's down up to 600 meters deep, and to reach that coal, there are very large systems for cutting out the cover. That is more or less sand, as you see on this picture. And let's try to understand that. So you have this sand, and this huge machines have to dig this and move the sand to a different place. That is a movement of matter that is hard to compare with anything else you have seen. And to give you an idea of the size here, you see this this is actually an active site here, and so, or here's another active site, and the sizes here, these are in kilometers. So we have many kilometers of digging there, and if your house was in that area or your town, then it is completely teared down and will be never show up again. After doing then the digging process here, the landsite is in some way recovered. So part of the stuff is going here, and they try to cover the area with water, lakes like here, or with forests, and with small hills, depending on the activity. So you see that is really cutting out a lot of land. And so this, for example, here is the city of Köln. That is one of the largest cities in Germany, and you see the size of the different open pit mines is definitely comparable to the size of one of the largest cities. Yeah, using a lot of land area for that. Here is another problem. This is about coal. Coal is usually not in Germany. That should be mentioned. In Germany, it was usually not produced by open pit mining. It had deep mining technologies, and so you didn't see too much at the surface. But there is a big problem due to the fact that if you have a surface and down there's the coal, then you cut out the coal, then the land is by the time lowering. And if you have the land below the water streams, so all this area will fill with water. But because there are living peoples and in this area there are houses and the houses are going lower, you don't want that the houses are flooded. So all the area that is painted here in this blue color are areas where you naturally would have lakes now. But because there are living people, we have to pump the water into the next river. That is a lot of work, and it's so-called Ewigkeitskosten, cost forever, because you have to pay for the pumping. And all the red dots are so-called pump works, so that are pumps that pump water into the next river. For example, here in this Emscher River. And because the river is now lower, you have to build huge walls to keep that river at place. And you bring the water up here, and that is the reason you have to pump. It's about 60 megawatt of energy you constantly use to pump the water uphill. That's yeah, significant amount. Other technologies also use land, and I've shown you a picture from fracking. Fracking is a technology where you can extend the amount of oil or gas, depending on the site, that you can extract from the underground. The fracking technology is mostly based on the way that you pressure water below the ground. That means you have an extremely high pressure, up to 3000 bar, as far as I know, so that the rock in this area deep down, maybe one or many miles down, is cracked, and through this small fish cracks, the oil and gas can come to the surface. There is one problem about the water pollution. There is some danger that you have water pollution, but if you are carefully, it's not really toxic, and it is usually not the core problem. But what you see here, this is, by the way, Texas. You see all the spots where they work, and typically you have these areas where you have to set up tower, and you have to use the land. So here you see large areas of land that are in use, or parts of it are in use, to produce fracking. In Germany, fracking is not allowed at the moment, or it has a very high security level. So Germany could do fracking, and by the way, we have enough gas in our underground for 25 years if we would use fracking. But for political reasons, this is not productive in the moment, depending on the rules. The United States was very busy, and they accepted that it may have some environmental problems. And it should be mentioned that after closing one of the sites, of course, you can cover it again with green land, and so it is not forever, not comparable to this ignite coal, where you have much more deeper problems in the environment. It's always a little bit funny in Germany. We accept that we dig the ignite coal, and we don't accept the fracking. That is, I don't know why that is, but it's the actual situation. Now, there is another problem with all the types of burning matter. If you burn anything, there's always some waste product. There is the air pollution. You can filter the particles, and there is always coming carbon dioxide out of the chimney. So the picture here is about the air pollution and the particles. So we are talking about particles at the moment. And particles are especially in areas of the world where you have not the environmental awareness or not as much environmental rules. So the coal-powered power station will produce a lot of it. And here, if you look into China, you will see that the amount of particles per cubic meter is at least 10 times or even sometimes 100 times higher than in other industrialized areas. Of course, if you are in an area where just only fresh air and forest exists, these numbers are very low. So a typical natural environment has particles in the range of 10 to 20. That may depend, for example, why do we have that on islands? There's some salt from the ocean that is in the air, and there is dust from the deserts, but it is not really a lot. It is in the range of from 10 to maybe 50. If you look into Europe, you will see that we have, in the moment, more or less clean air. There are some parts, especially in cities, and where the pollution is higher. For example, with cars, and cars produce different types of pollution, like exhaust gas that we usually filter today. There is also a little bit coming from the brakes and from the tires. So that is not a really complete clean thing to drive cars. It should be mentioned that this is a shoot of one day. So if you want to see what's happening today, you can go to that website and you can see the actual situation. So for example, if there's rainy weather, we have a very low density of pollution. If we have, for example, in winter time, when there is not a lot of air exchange, then we'll have high levels here. And you can imagine that breathing then in these areas is not really healthy. And it's clear, so beginning here somewhere it's unhealthy, it's really dangerous to be in places with 1,000 particles. It's a little bit, if I want to compare that, if you are smoking a package of cigarettes a day, that is this level here of air pollution. So in some places you have that. I've been to that area, by the way, in Peking, and you immediately start to joke because it's not smart. So if we look into air pollution, we can ask what is in the air, what are the typical pollution emissions, and there are very different types of pollutions. There is sulfur that is strongly related with energy conversions, as you see here. And so energy conversion produces a lot of this, produces a lot of the disasters here, especially in the range of sulfur. That is the responsible part is the coal, burning coal or burning bad oil. It sometimes also contains sulfur. In Germany, for example, we have extremely clean oil that or diesel and petrol that has just no sulfur in it. Then you have the carbon monoxide, that is a dangerous gas that really can kill you. And then there are the different types of particles. There are different measurements of particles. It depends on the size of the particle. Very small particles have the danger that they go into the lung and may you may end up with cancer. Larger particles can be exhausted by your lung by choking, and so that as smaller the particles are, the more dangerous they are. That is not first moment intuitive. So there are always some, there are also some non-energetic areas where you have pollution. Even agriculture pollutes something. There's, for example, NOx that is due to the animals, livestock. You have waste in burning fields. Here you produce carbon monoxide. That is happening in some areas. If you burn the savanna, it will get really high, and forest fires are also a problem. And we see that in some areas of Africa and South America at the moment. Now, but go back to our industry and energy industry. International shipping is significant pollutant of sulfur and NOx, but the sulfur is really, you see that from the satellite pictures, there is a sulfur streak around these large container ships. Today there's a tendency to reduce that by burning clean diesel, but yeah, it's a little bit more expensive, and so they don't do that. There are no really international rules that can be enforced. Transportation, producing a lot. Cars, industry, also a lot of this here, and so on. Now, if we look into the different trends in air pollution, we see that things are in some areas changing. And first of all, look into the air pollution by the OECD countries, that is Europe and United States and Canada, also the more or less old industrial countries. And you see the pollution has gone up till 97. That was the moment when people did not longer accept this dirt. And since then, the air pollution, especially on sulfur, because sulfur you can really see has gone down significantly. That was by a filter technique, especially for huge coal power plants. In NOx, that is usually coming out from cars. You see the OECD countries stabilized in the 17s, and now we have even a little decrease here. Black carbon is since a long time going down, so because people see that, they don't like that. Organic carbon is quite very low now in OECD countries. Carbon monoxide is also going down, and other chemicals are also going down. But that's not true for the whole world. So there are some areas in the world that produce in the moment more, and that is especially Asia, India and China are the top players here. And you see the international shipping. So ships are really producing as much sulfur as, yes, say half of that the OECD country, only for ships on the ocean. That is a huge amount. And other areas, Asia is also very busy in the moment, and so we produce a lot of this exhausts, and hopefully they will go on the same track as the OECD countries and stop their air pollution.
Now we have to discuss the greenhouse effect. The greenhouse effect, first of all, is really different to the other pollutions because the greenhouse effect is a long-lasting effect. Pollution, as the visible pollution from power stations and cars and so on, disappear within at least 1 year due to rain and other effects. But the greenhouse effect itself is a very long-lasting thing, and so to understand where really the core problem is, I want to go a little bit into the detail of the physics, because there's so much strange information in the web and so much arguing about it that there is no greenhouse effect or the effect is not true or whatever. So it is the easiest way is really to understand what's going on. And so there are two things. The one thing is energy is coming from the sun to the earth, and it has a radiation, and this radiation is 341 watt per square meter. This is without discussions. You can a little bit discuss about the energy. Is it changing? The sun is more or less a stable, very huge stellar object and has not strong fluctuations. It is true that there might be some years with a little bit more or a little bit less. That is due to the solar cycle. But over the last centuries, there was no significant change here. And today we have satellites in the orbit and special satellites for the sun that measure that number as precise as possible. So we are quite sure there is no more change than only in the last figure, and that is not a trend, but it is only a small deviation of F over maybe 11 years for sun cycle. So this energy then makes a difficult path through the world. And to understand that, we have to look what's going on. So the first part is some of the energy leaves immediately because a cloud is in the air, and cloudy days, you know, are not that bright, and the cloud reflects the sunlight back into the universe, into space. And another part of the light is reaching the surface, but is reflected at the surface. That is, for example, on white surfaces, very strong, buildings, sand, but most of it is ice and snow. Ice and snow reflect sunlight 90% or even more, and so they are very effective to bring this energy away. So finally, there is 161 watt per square meter absorbed by the surface. Absorb means heating up the surface. And now the things get a little bit complicated. One part of that is thermally going into the atmosphere. Some energy is used to evaporate, for example, water and generate new clouds. Some of the energy is going into the atmosphere by radiation, a similar process, but the radiation is not directly going into space. There are some blockers. One blocker, of course, are the clouds again. So the clouds bring something back, and the greenhouse gases. And that's the point we have to understand. The greenhouse gases bring the radiation back, and so there is only a smaller part directly radiated out then. And this radiation that is emitted by the atmosphere and is emitted from the surface, this cools the Earth. This is a cooling effect. Now, if you want to have a constant temperature on the Earth's surface, the incoming energy and the outcoming energy has to be exactly the same. Otherwise, if they are not the same, it will heat or cool the Earth. Now let's look into the numbers. We have 341 coming in, 120 is directly reflected, so we have finally 239 that is not reflected, that is radiated into the space by the thermal radiation. This thermal radiation is now very strongly depending on the temperature. So that means if you change the temperature, the radiation is changing. So this number here is strongly dependent on the temperature. On the temperature of the surface here. and of the atmosphere. So this temperature can go up a little bit if more energy is directly going back here. If your energy is not able to go up there, you have a back radiation, and if this back radiation is going up, then the temperature is rising, and because the temperature is rising, you have a feedback that you radiate more, and you again stabilize the temperature. So if we put greenhouse gases like carbon, CO2 into the atmosphere, this arrow here is getting a little bit larger, maybe a few percent, but that has a big impact, because then we have to have a higher temperature, that we are in the equilibrium between incoming and outgoing radiation, because this incoming is constant. So this has to be changed due to this cycle here. So that is the core point. It's a little bit tricky physics because there is many factors involved, but we understand that very well, and this is more or less known since the 19th century. Arrhenius was the first one who was warning that there will be a greenhouse effect if we burn all our coal. Now, to understand why carbon dioxide is so interesting, we have a little bit to understand what's coming in. From the sun, at the top of the atmosphere, there is energy coming with all frequencies, from very low, 250 UV. Then there is something absorbed by ozone, so we are not killed by this hard UV. That's very lucky, otherwise life would be very hard on the surface of the Earth. And then you have the light, the visible light. It's more or less here. This is the wavelength of the light. So we are looking here to our sun. And now there is a long tail in this radiation spectrum, and there is especially this area here is heat radiation and thermal radiation. And thermal radiation, no, let's write it down, thermal. Thermal radiation is this radiation that brings energy back into space. So, and there are some areas in the spectrum where the carbon dioxide is active and will cut this window or close this window of radiation. So it's only a small part, but it is a change that has a big effect, because if you put 1% less energy back to the space, you have a strong heat up effect. Of course, water also has a strong effect. As you see, water is here. This is water, this is water, this is water. So, water, even here. So water has a much stronger effect, but water is always here, and we are in equilibrium with water since billions of years, at least millions of years. And so this is the change here in this area. It looks small, but small changes in temperature have a big effect. Now, here is a picture that goes a little bit more in the detail of the so-called water vapor window. This is the so-called water vapor window. Water does not absorb in this area, but the carbon dioxide is absorbing in this area. So the carbon dioxide is closing a part of the so-called water vapor window. You can calculate all those numbers, how much watt per square meter this effect is. Remember, this was a visible light that we can see. This is the light that the black radiator of the Earth brings back. And so again, the radiation of a body, it has spectral color. And especially the sun, this is the sun, this red line here. And this is correlated to 6,000 Kelvin. That's the temperature of the sun. and the temperature of the Earth is around about 300 Kelvin, and so our radiation is different. These shapes of these curves are very well known. That is very interesting physics, and this is defined. There is no discussion about these curves, luckily. And this absorption is also known. What is not exactly known is how much carbon we will have in the future. That is depending on our habits, how much coal we burn or other carbons we burn, and the exact change in temperature due to this change in the window. Because there are many other feedback loops like more clouds and less ice and something like that. That is very, very difficult, and then we have computer models to calculate that. But the simplest thing is, what is the first guess? And the first guess is you definitely reduce the amount of energy that can go back to space, and that has finally always an effect in changing the temperature. Now, what's going on now with our carbon? So this plot here started 1958 at Mount Loa in Hawaii. Why did they measure the stuff in Hawaii, and did they like to have a nice holiday in Hawaii? No. The reason is this measurement was done in the middle of the Pacific Ocean. That is a place far away from any natural sources of dust, of carbon and whatever. So that's a very good place to measure more or less the mean carbon dioxide concentration. It would be not a smart idea to put this station in the middle of a big city like London and then measure, because then you have a lot of local effects. We want to understand the global effect. Now what they did is they measured this curve, and you see the blue curve, the shape of the blue curve, and this blue curve is a mean over 1 year. But if you look within 1 year, you see that the dots within 1 year are not really constant. They're going up and down. What's the reason? There is the springtime when the plants start to have new leaves, and then during the summertime, beginning in May, they absorb a lot of carbon until October, when the leaves are falling in fall. And then there is no more absorption by the nature, and so this effect of absorption by the trees has about an amplitude of about 2.5 parts per million. Now, one word about this here. This is it's micromole in mole, but that's the same. That is part per million, or we can write it in micromole. Micro is a million, mole by mole. No, don't go in that detail, but it is not something very strange to someone who studied chemistry or physics. So you see every year, and you can count for years just simply by counting these peaks, but you have it much easier if you look into the scale, the time. And so within the last 60 years, the amount of carbon has started with about 310 and has risen now beyond 400. And that is more than 60 or 70% more than the start. And that is huge. That is huge. So the carbon in the air is more or less 50% completely produced by human activities. There are different activities. One thing is, of course, burning coal and oil and gas. The other is burning down trees in the tropic sphere, or whenever you burn a tree and wood. But trees usually come back as long as you don't generate wasteland. And so most of the effect is by the carbon. And interestingly, if you look into some places here there have been some years with not that strong increase in carbon. What was the reason? The reason here is that was East Europe and the Soviet Union broke down, and they had teared down their old coal-fired plants. That really is a visible effect here. And then if you go very, very precise in here, you can see very small effects for economic crises as 2001, and you can see them also in 2008, but they are hard to see here. So this is not a completely constant, it's a little bit also modulated by economy, but that gives us a good hint that it is real, the source is real industry activity. I did this plot here, you see the concentration, and I did a calculation about the best fit to this curve, and you see there is this deviation for the beginning of the 90s, and so we can see that the economy is more or less plotted in this carbon line. So whenever this line is up here, economy is very strong, as here, beginning of 2000. And if there is a crisis, or they shut down a lot of old industry, then it's going down. So there was this shutdown of old coal power in East Europe and Soviet Union and Russia. And here was the economic crisis of 2000. And here we say the 2008 crisis a little bit. And yeah, how this will continue, we will see. Why there is this modulation here, I actually don't exactly understand. There seems to be an additional cycle that maybe this, yeah, I don't know. Maybe you can find that out here. I have never seen a paper that discusses that. This line is done by myself, so that was a calculation I did on this carbon problem. So now, does the temperature really change due to this carbon problem? Yes, that is also a very difficult thing, because on the long run of the history of mankind, we have usually no thermal measurement instruments, and so we don't know the exact temperature, maybe in the year 1500. And it is not that simple. If you measure the temperature at one place, it may be a special place that has just a few years with very low temperature, and then you have to measure that over the whole globe. So there has been a lot of research, and before 1815 there is more or less only an indirect knowledge about temperature. There have been a very few thermal measurements in Britain and some other places, but they are hard to understand because it's not that trivial to measure within a small change of half or less than a degree. So since 1850 we have a standardized measurement, and so we have this red line. Then there are now satellites in the space, so we can now measure much better. And different authors have a little bit different results, but you see the difference is maybe something like 0.1. It is not much, so the uncertainty is quite small. And if you look now back to the 19th century and compare that with today, you see that we have about 1 degree Celsius more. But we should mention that maybe that we have a thermal minimum in this time area, so maybe the thermal normal is here. So if I usually put the thermal normal here, that was the time of the first half of the 20th century. And so since the 60s, we see now this very clear way up. So now it seems clear that it's going up. That is the problem. And we see that not only in this temperature measurement, we see that also in the measurement of glaciers. Glaciers are sensitive to temperature because if it's a little bit warmer, glaciers melt and they get smaller and shorter. That is easy to measure. And there are also a lot of reports from historic sites how the extension of glaciers have been. There are other things like flowers, when flowers start and so on. So we have a lot of measurements and all the indicators show since the last 50 years up. So it is clear that there is a correlation, and due to the line of discussion I had with the physics behind that, it's not only correlated, this is really depending on the carbon exhaustion. So there are other factors, for example, volcanic activity. So if there is a big volcano, then the volcano will cool down the Earth. And so if you look into history, especially at time beginning of the 19th century, 1816, there have been huge volcano eruptions, and these eruptions cooled the Earth, and you see that is a really strong effect, about 1.5 degrees Celsius. That is a lot. So imagine that, and that has been in historic writings the year without a summer. The people could not harvest, and that really was devastating. So people get hungry because you didn't have anything to eat. That has been a very bad time. There's more volcanoes in this area. In the last century, we had not a real huge volcano eruption. That should be mentioned. It is possible that one of these thousands of active volcanoes on the Earth is blowing a lot of sulfur and other smog into the atmosphere, and there is a short-term cooling effect that overruns the general trend of warming. So we know about these volcanoes very precise, because in the modern time we can measure precise what's happening with the volcano. Actually, it is not exactly known what volcanoes were involved in this event. Maybe they were in the Antarctica, no one was there, and so it is a little bit mysterious what volcanoes really were here. Some of them are known. Indonesia is well known, and Indonesia here is was in Indonesia. Krakatau volcano was well known. And then you see, by the way, always after that the atmosphere clears up, and there's always the same type of cleaning the air within 2 or 3 years. So that's a short effect, not a long-term effect. That's also similar to standard pollution. So if we have pollutions with ships and whatever, the pollution is short-term. So if we would shut down our industry within 3 or 4 years, the sky would be clear, not the carbon problem. The carbon would stay. Carbon is long-term. So why is this now a controversy about that? So some things are widely accepted. The first thing, carbon is produced by our civilization. No one can say we don't burn coal. We know that we burn coal, and we can exactly calculate the amount of coal and oil and gas for every year we burn. And so we can measure that, and so we can see exactly that we have produced a lot of carbon in the atmosphere. If even people who don't like this climate discussion will agree that there is a change, because it's measured and it's more or less plausible because you burn the coal. The second thing is the carbon has an influence on the radiation balance. That is physics, as I described at the beginning, and so it's hard to discuss against that, because then you have to ignore physics at all, and that doesn't make too much sense. We can see this law, everyone can measure that. If you have a little bit of equipment, you can measure that carbon is absorbing thermal radiation. So that's not a big discussion. And we can measure the temperature of the last 70 years because we have worldwide weather stations, and more or less the weather stations are showing a trend upwards. There are few, very few with a different trend, but you can say, okay, the cities have grown and weather stations are not that far away from the city, so it might be a local effect additionally. That is true, but there have been a lot of care to calculate these details. So this is widely accepted. Yeah. Now then there is something unclear, and that is the future. What will happen in the future? The future is always very hard to predict. And so the problem here is, because if we say there is this carbon effect and we have to reduce the pollution and we have to reduce oil and gas and coal, then you hit the industry very strong, and especially the companies who sell this stuff. And so they try to show that the future is not directly in danger. And the first thing is that you say the climate is a very complex system because there are many things working together. The one is the clouds. As we have seen, the clouds have a very strong effect what energy is going back to the space. We have the ice, and ice is melting at the pole, and so we know that ice is reflecting light, and so it will accelerate the effect. Wind is difficult if the temperature difference between north and south is less, and that makes sense, then the wind is going down. But if you have more temperature on the sea surface, you will have hurricanes. That is strong wind. So there are two different types of wind, and that makes things even more complex. And the ocean is transporting a lot of energy by streams, and so the Gulf Stream may go weaker due to different temperature at the north area and the melting Greenland ice. That is hard to measure. Computer models are not perfect. That should be really mentioned. It is very hard to do that in a computer model because you have to manage all these very difficult variables, and all the predictions depend on these models. So if your models are not perfect, your predictions are not perfect. And this is the one case that people say, okay, there will be no change, or the change will be not very strong, although we already see that there is some change. The second line of discussion is that people say, okay, what's the problem? A higher temperature. Why should be there a problem? In Furtwangen, we will have a climate that is as nice as down in Freiburg, and then where's the problem? It is true that the temperature that is going up is not that a big problem as if it would go down. I think if we would have decrease in temperature, then we will go back to an ice age, and that would be, of course, a complete disaster. Higher temperatures, but have also a big problem. One thing is the sea level rise, and most of the cities are at the coast, and so they will have big problems with the seawater. And some deserts may or may not grow. That is hard to predict due to the problem of the computer models. So, and the most dangerous thing is this so-called positive feedback. It may be that if the temperature is rising, additional effects like the melting of the ice or methane in some areas of the north is going into atmosphere, and we'll have not only a 2 degree rise that could be acceptable or something, but we can go far beyond that, maybe 5 or even 8 degree. That would be absolute not easy to manage. So be careful with our planet. And this controversy is hard to solve. Finally, we will know what happens, and we have to be careful. Some ways to look in the history of the planet and ask what happened in the last millions of years. And so now be careful. This is a plot that is really special because it has here 500 million years ago, and then this scale is logarithmic. That is unusual. Usually the other part of the scale is logarithmic. So the years are logarithmic. This is a thousand years, so it is a million years here. It is 20,000, and this is today. Now, if we look into the temperature, we see that aeons ago, the time of the Saurian that ended about here, the temperature was about 6 degrees higher than today. So the climate was very, very different. There was no ice cap at the North and the South Pole, and there was tropic climate even in our area here. So in Furtwangen you had palm trees and all that at that time. And so the Swabian Alp here is shelf ocean with a high temperature. We can know that very well. And then temperatures have gone down, and they reached a very low minimum about a million years ago, and ice was growing in the north areas, and we have seen this ice ages. And an ice age is the time when you have temperatures 5 degrees deeper than today. So then ice will grow from the north and from the Alps down into our common places. And the last ice age here ended about 12,000 years ago. And then we have now this temperature over more or less 10,000 years. And typically every 10,000 years we have a new ice age, so the standard track would go now down. But what we can measure here is our temperature in the moment, and maybe the temperature is going much up. We don't know. These red dots are not completely reliable, but they could happen if the carbon problem is not catched. So we will then be in the temperature area as Thesaurus there, and maybe it's not a nice thing for humans, but yeah, you see the long term. It should be mentioned that measuring the temperature over this long historic times is not trivial. There is a lot of guessing and big discussions, but what is absolutely clear is that we had these ice ages. There is no discussion about that and about the temperature then. That could be measured easier, but the very early times here in the Saur age, quite difficult. Now, what happens to nature if temperature changes and if we have a carbon change? The interesting thing is this map, and this map shows us how large the leaf areas are. So how many leaves could we see from the satellite? And that can be measured quite precise due to the chlorophyll in the leaves. And what we see in some areas, you see a dark green. That means we have more plants than 40 years ago, and especially also in Europe. You see small spots like here, they have less. But if you sum all that, you see a result that we have a plus about, depends on the calculation, but we have at least 10 to 20% more leaves today than we had 40 years ago. There are two things that drive that effect. One is the reason is carbon dioxide. Carbon is food for plants, so plants have it easier to grow even under restricted water situation, and higher temperature is an advantage. So we have the greenhouses, and greenhouses are built because we want to give the plants a higher temperature, especially in the north area where you see very strong effects here. the temperature effect is strong, and I think in the south areas we see the effect of the carbon more or less, because in the south the temperature change is usually small due to the radiation is a little bit different than at the north areas. So that is an interesting thing, because it tells us nature can handle the problem. If we like the change, that's a different thing. So now what can we do? We can change our carbon emissions, and we can look for carbon neutral sources. So we have here our list of our main energy sources, from a gas combined cycle to coal and solar. And so we can look into the cost of the systems. And the price is depending on two things. The one thing is the fuel. So gas combined cycle has a low carbon emission, but it needs a lot of fuel. If the price of the turbine is very low, the same is not exactly, but with coal and advanced coal, the investment is not too high. Much of the money is going into waste management and into the fuel. Very different in carbon free. So this here is all emitting carbon. Left of that we have no carbon, or not so much that we should mention it. There is nuclear power. Nuclear power has just no fuel cost, because the uranium is really cheap compared to the cost of the capital. You have to build a very expensive site, and things get even more expensive if you build solar, because you have just only to build that, and operating and this is operation cost and maintenance is low here. So keeping the things alive. So the highest costs are here in nuclear. You have high environmental questions, high precision, expensive workers, and so on. But solar, yeah, if you put that solar on your roof, you don't have to care too much about that. And if you put the solar in a desert or so, it is running for a long time. Should be mentioned that in some areas you have to clean the solar cells. Wind needs a little bit more of care. So wind is a mechanical system, and so you have to look if the mechanics is still on. You have to put oil in there. You have to care about the tracks and so on. That is a little bit more expensive. So what to do? Yeah, maybe we can reduce the greenhouse gases. But what greenhouse gases are in there? So we have a special look into the main greenhouse gases. Usually people only talk about carbon. Why do they talk about carbon? The reason is carbon is long term in our atmosphere. That means we cannot shut down the carbon production and hope that within 5 years things are back again. So what we do today will still be in the atmosphere in 100 years. If we emit another strong carbon gas like methane, this carbon gas will not stay forever, maybe for 10 years, and then it's gone. Why does methane go away? The reason is simple. Methane is a gas you can burn, and due to lightning and thunderstorms, this methane is burned by the oxygen and by the way producing some carbon, but that's not the core problem. So we can look how much they produce in petagrams and teragrams. Be aware these are two different scales here. That makes it a little bit strange, but you can calculate the total emission, and they are numbered here. So many countries now look for change, reducing the carbon emission. so of a change in carbon in the electric production, for electricity production. And what happened during the last 10 years? The interesting effect is one country really stands out here, that is the United Kingdom. United Kingdom has reduced its carbon emissions stronger than anyone else in the world. What did they do? They shut down their coal-powered plants, and instead of them they used many gas fueled, methane fueled power plants and wind energy. So a little bit of solar. So how did they do this? They said, okay, we have a tax on carbon. So if you emit carbon, you have to pay for. And within a few years, the industry really changed that, because they say, okay, we don't want to pay for that. And so they produced the energy just carbon free. That is impressive. And that also gives us a hint how strong a carbon tax can change the habits. So other countries here, United States, outstanding, because this scale not only shows the change here, it also shows how much it is. So it is multiplied here, and the area is what they saved. So China changed the amount. United States and China reduced that, the carbon emission per kilogram. So this is per kilogram, the carbon emission in grams per kilowatt hour. So both of those countries were very successful. Other countries were not that successful. So Germany, for example, was not as successful as China or United States in doing that. Although we usually talk a lot about Green Party and green energy, we were not the most successful country in this scale here. We have reduced a little bit by our wind and solar powers, but what we are doing now is we shut down our nuclear powers, and that will produce, and that has to be produced by other means, and usually they do it by coal power, so we are not on a good track here. Some countries in the world did not reduce their energy, the carbon emission per energy, especially Brazil, India, Japan and Indonesia. Japan is a special case because they had to shut down their nuclear powers. India is a developing country and has not enough resources to do that. Here, South Korea has strong industrialization. It has problems to use wind energy because there are no sites there. And so we see, luckily the big guys here reduced the emission, and Germany did also a little bit in that direction. So the long trend is the primary energy carriers in carbon, and so the kilogram of carbon emission, that's more or less the same scale. It's how much energy, how much carbon you produce, so carbon oxide or CO2 per energy. That's the point here. And so the long-term trend here in this picture shows us that it goes down. And there is some deviations if you include biomass. Biomass use is going up, and so that is the impact of that. Our target should be that we are down here, and so yeah, since a few years this is not going down any longer. The reason are these countries with more carbon production.